Okay, we're electronics design. This is the microcontroller. This is the same. This is the same microcontroller that we used last year. It's the same as PDR. The microphone. I like pointing. All right. This is the same microcontroller that we used last year, and it's the same one that we presented at PDR. The only main difference is nothing.
We are using the TPSM 5-volt converter that just steps down from whatever the battery voltage is to 5 volts. And we did some calculations to verify that like the resistor values we chose were going to work out for the output voltage, which we found they did. And those worked out. Those provided the same like results that the web bench report provided. So we're thinking we're all good there.
And then we have the 3.3 volt DC converter. We're using the TPS 82085. Just a synchronous buck converter. It'll step down to 3.3 volts from the 5 volt regulator. We did more calculations for this one as well to ensure that it was outputting the right voltage, and we calculated to output 3.2757 volts, which matches the VBench report. For our battery connector, we have a fuse and diode going in, and we have a voltage mux, so we can pick between USB power or battery power, and we are going for a fully segmented design.
Just so the segmented design, you can see it here, where you have jumpers breaking off different sections. It's a pretty straightforward design. It's tightly packed. The components that need to be close to the ICs are close by. And then as well as two test points to directly inject voltage. Same design as last year, essentially, with 2 different ICs. And the benefit is the past ICs that we've been using are like not discontinued, but they're not well found anywhere. So we switched this one, and it also gives us better efficiency. The USB and SD card, we're still using a USB-C that we transitioned from our 3 stack board that we had like 2 years ago. So that's all the same. And then now we're using a SD card that's the push type instead of the hinge design. It'll be positioned. I'll show you the picture in a second, but the lines have pull-up resistors. That's the current orientation of it. Right now, where it's on the end, it'll be positioned towards the top. If you look at any of my designs, there's like kind of a top, and it's on like the back side, so you can probably push out the SD card from wherever it's being housed, opposed to the previous year where you would have to like completely like disassemble the av bay to even attempt at removing the SD card. Since PDR, we've transitioned away from a few of our sensors. I think this is one of the ones that we did keep. This is just one of our IMUs that's being used for accelerometer and gyroscope. Those are the parameters if you care to look. Basic schematic drawing with decoupling capacitors that'll be placed close by to its power pins. And then all of our sensors are being ran on SPI opposed to I2C, which was presented at PDR. This is the ASM 330. It's also another IMU used for its accelerometer and gyroscope. Those are the parameters, similar to the last one. It has decoupling capacitors, and then a separate one on its VDDIO pin. And this is one of the ones that ends up having one of those bigger capacitors on it. There's going to be 2 on this design. Those are the parameters. We opted to end up switching a few of our sensors around, and now we have a dedicated magnetometer chip. Those are the parameters if you care to look. Again, it's similar schematic design. This is the pressure sensor that we're also using for a temperature sensor this year. This is the same one that we used last year. Same layout, SPI, and then those are the parameters.
But because we're using SPI for the sensors this year, we're also going to need OR gates for each of the sensors. This is because the sensor shares the data input between its SPI and I2C protocol. And when the microcontroller trying to transmit to other sensors, it will pull the chip select pin high, which will bring it into I2C mode. So we don't want the data that the microcontroller is trying to send to other chips to accidentally be a valid I2C command. So the OR gate pulls the data in to always be high, which won't be valid.
And then last, here are the low side NMOSs. This is just for configuring the microcontroller in such a way that it can power higher amperage loads, like I believe the camera here or anything else, using this chip here. It's the IRF chip where it can take up to, say, I think it's around 12 amps. Yeah, 14 amps. Sorry, I should read my own slides. But this is very similar to what we had at PDR. It's just a slightly different chip that can handle more amperage because we need it.
Next, we have the GPS. We're still using the Tessio Lib3F, which is the same as PDR. And at PDR, we said we would use I2C, but we're switching to primarily using UART, but still hooking up the I2C as a backup. In addition to GPS, it also needs an amplifier and a filter. We did switch the filter because the other one from PDR was out of stock, but it has very similar characteristics. And then here is some pictures of the GPS layout. And we made sure to make sure the traces stayed short and they were impedance matched and via fenced.
Transitioning to everything that's now like off board through some sort of connector, essentially. Integration, we're still coordinating with the different sub teams. This is 30K as an example. Down here in the green is the Mars board with its connectors that you'll end up seeing in a few slides, which will then hook up to a connector on this blue board, which is the Phobos board, where the radio module will be housed. The design didn't really change much from this aside from the connector being placed on it.
Yep, so the radio is the same as PDR. Has a expanded range from last year. Yeah, and it's connected to an SMA connector. And here's the layout for it. So the big square is just the radio, and then the SMA connectors on the left. Yeah, and there's the Mars board connector on the bottom. And yeah, we still need to work on impedance matching for the antenna.
Wait 1 second. So this is the 3D view. It has all the labelings on the outside just for easily being viewable. And there's also pads if you wanted to probe the 3.3, for example. And then there will also be a polygon for ground on the top.
Yeah, and for the PWM, we need level shifters to change from 3.3 volts on the microcontroller to 5 volt PWM. So one of these level shifters goes to the servos, and one of these goes to the encoders. So the encoders are an input and the servos are an output from the microcontroller. And so port A has a range of 0.8 to 4.5, so the 3.3 volt always has to go on port A. But this level shifter automatically detects an input or output. Yeah, and it should be fast enough to handle PWM. And we also have, we're working on a wiring harness for going between the battery and the Mars board and the servos and encoders. So the harness will have to branch out 4 ways, going from 7.4 volts on the battery to the 4 different servos, because the servos are using a higher voltage. And the encoders get, they need 5 volts, and they get that from the Mars board. And the PWM signals are also supplied. And then there's also a MOSFET for disconnecting the power from the servos and the encoders in case there's any problems, and it can be controlled by the microcontroller. And for wire sizes, we have 10.4 amps from the battery, so 18 AWG should be good for that. And then we could use smaller wires on the branches if necessary.
These are our current power calculations. This is just the Mars board, not the any of the rover stuff included just yet, just in case things move around there. Currently, that's its need for milliamp hours. So basically, 2 18650 batteries will suffice. This is useful for some subteams. This is just the layout and placement of the different sensors, GPS, and the SMA essentially. The only thing to note on this is that the GPS module seen on the right here is on the bottom layer opposed to the top, which is where all the rest are found. And then also that there are pins designated which ones are pin ones, and you can get the correct orientation of the axes. All right, Mars board. This is the 3D view of the whole thing. You see the microcontroller in the center. You have the sensors up at the top, just like last year, and then payload and XV connectors on the left-hand side. Power's at the bottom, similar to last year. We're still looking into a different connector for the battery. Before it was a XT30 connector, I believe. And we're just looking to shrink it since the board in dimensions did shrink from 69 by 69 millimeters to 50 by 50. Again, that's the USB-C at the bottom. And then right here where you see all the vias is underneath where the GPS is. These are 2 different views, a more angled view so you can maybe better see the test points. And then also the 90-degree angled surface mount JST connectors. This is like the board layout. A few things still need to be routed, mainly both connectors over on the left, just while we were replacing other things that are more prioritizing. That'll get placed. I don't see too many problems. It'll be difficult to get a few of these traces around this bend over to where they need to go. The air brakes, that connector has not been in place, but we can transition to a surface mount one instead of a through hole and utilize the area that's taken up by the GPS on the bottom half. And then also, if there's any room for extra GPIOs, we'll throw them on, but no guarantees. Questions? What? Oh.
No, okay. I actually understand the app, right? Base for each of these rockets look like this here, like replacement for the SMA connector. It being.
Oh, I'm sorry. I didn't clarify that. Where did I do integration? These, so in my design, I kept it as a straight up and down one. The footprint size where the holes are placed, regardless of if it's a 90-degree or straight up and down, are all the same. So just to pick and choose based on the different locations that it might have to be in, I just left it as a straight up and down. But for at least 30K's case, it's a 90-degree connector facing that orientation, and they have the freedom to choose straight up and down, left, or down. And then the Phobos board kind of has to stay sticking out in that direction, or you could go straight up.
I just wanted to share just so we don't run into any issues. That's like 60 seconds of layouts. Like what? Some of the traces, like I think it was science center. That's kind of aware and stuff.
Slide 7.
I just want to like clarify, I guess, check to make sure I know the traces that are touching that we lost to. I guess it's. Yeah, okay.
There's DRC, and then there was a problem with when we ordered the second round. There was a via that was moved, and that bridged all the traces, so we rolled it out.
Okay.
There was no like issue with the board. It was just when we sent it to the fab, I moved a via while Dan was ordering, and then he needed it again, and I didn't reflow all the planes.
Okay, I just want to make sure.
No, you're fine.
And then for the SD parts last,
Yep.
why did you change to the, I know it's just one annoying to get out. But is there anything so like the SD part might be able to migrate out of this one?
No.
Can we ever use this one?
It's a push. It's like you have to push it in to get out, and you have to push it kind of
Yeah.
hard, kind of like things like camera one, you get like push it in. I don't think it can vibrate out really.
It's like, I personally had an SD card migrate out of my phone.
Okay.
So just something to keep in mind. I like, doors are complete much this or that, it's just they are meant to be. Like,
Yes, I can also look into if similar ones have the same footprint, because then we can just put on an hinge type if it does
let's say
become that.
like some sort of, some sort of. But. I don't know.
So if the SD card is sitting in the thing and there's like a big acceleration in the direction, you could like push it.
More also think it's like, when we hit the ground or we come parachute, it's like a rapid launch course. It is jets, well, it's trying to write data, you use the data now. Like, yeah, that'd be really bad. Like, yeah. I don't know, I was just maybe.
I know there was want to switch to a push, but I'm happy to switch back to
No,
it.
I think it's a good idea because it was annoying for me to have to answer the
Exactly.
Like, I would rather answer this more simple times than,
Have it fall. Yeah. Yeah.
entirely, so.
Just have to screw it.
Like the app bay was just like pressed up against it, and the SD card.
Just, we can, I just like to make sure before we fly that it's like, for sure, or maybe we do some sort of testing on it, that's not true. Not sure, like, you know, see, it's as well.
Okay.
And then for the, I just out of curiosity, you guys talk about some of the new sensors you're putting on. How many of the sensors this year are new? Are they all basic?
I'd say 2 are new out of the 4.
Okay, and like they've all.
I believe so, yeah.
Basically, looking at the device that we were given from INPP, there actually literally has the exact same sensor.
Okay, cool.
That are like just by completing one
Well,
sensor,
that's good enough for you guys.
it has the exact same sensor.
And then my last one for the slide.
Slide 25.
So I know most of the run times are like an hour max. Is there like,
Wait,
at least maybe the, first of all, like, oh, maybe.
Slide 24. That's right.
Yeah, it's fine.
Yeah, I can change those because even with the safety factor included, it's still fine, but I'm happy to move up the
I would just. maybe
money
it's your
period.
Yes. Nice to have a higher time, just in case. If it is driving away.
Okay.
That might be the only one, it might be nice, not so much.
How much? Do you mean number?
Like,
I don't know.
can we get like 3 hours out of it?
Maybe.
Well, another thing to keep in mind,
Like the radio is, no, we can definitely. I was thinking probably it's like the radio is like the major contributor.
That would just be one of my concerns, like, if we lose
Oh.
GPS on it, for whatever reason, it didn't shut down.
Yeah.
That one's.
what I will say, the radio module.
Takes like 50 times. faster.
Well, yeah, well, I was gonna say, the radio module, like, you're designing for it being on the entire time, which is good. But in reality,
We're gonna use the radio modules.
yes, but we can, this is if the radio module is transmitting constantly. Like, we can have it transmit once every couple
Maybe
seconds.
like, this might be something more for programming, maybe after like 20 minutes, because it's like 100 to 7 for 30 seconds. Like, we're not gonna be driving it after 20 minutes.
Uh-huh. And also there, we did tie all the interrupts to these pins so they can go into a sleep mode where their like current consumption is like in the microamps.
Okay.
And it's extremely negligible. I don't know what really radio module is for its sleep mode, but
Yeah, so like a package, you can put the whole thing to the low power.
through the aux.
Yeah.
Okay.
Yeah, so the whole thing in the low power.
That is tied also,
Maybe
so.
if like if it doesn't hear from us in like 10 minutes, it goes into like a power saving mode. Maybe if we use contact, but we still.
The current,
Measure the battery voltage. Is that something like that, or sensor? Just real quick.
oh,
Like-
sure.
Because then we could turn like the motors off and just save the rest for GPS. It would be nice to know our voltage, like you don't have pad, you can. Just
Yeah.
the speed.
Could be.
Like you have to switch.
So one more time.
Yeah, an AC input. Right, it's space for.
Minimally, but yeah.
You need like a couple resistors.
There's something.
Yes,
but.
Thanks.
Sorry. Well, how much, the power going to the propane on the board, is that just for the monitor sensors? What?
You mean like the,
Connector on the monitor. How much current is going?
whatever the battery is, like, that's like full of like whatever is connected to the battery, and we know to tap out to like your harness, or the harness will, I think, get split from the same line. It's just that this is getting battery, whatever else is also getting batteries.
I just want to make like, for the drive motors and probably our servos, we would split off before going through the board. Right? Not supplying battery voltage.
Yeah. We're only supplying 3.3 and 5 volts out of the big. It'll be fun to wrap that up.
Maybe I missed it. How many MOSFETs are you planning on adding for those two? And so,
They're big.
yeah, I know.
I don't want to put two.
Well, no, one I'm just thinking, so there's one for the video, and then the other one is like.
There.
Yeah. In case we need.
Nothing. I was thinking about nothing. Don't worry about it.
Well, because you also mentioned another MOSFET somewhere else. Oh, for the GNC.
We only gave the camera into.
Like the one in the harness?
Oh,
But is that different?
that is different.
Yeah.
That's different. Okay.
Yeah.
Okay, yes, it's just, I was just curious.
I didn't put the pin configurations for like setting up the microcontroller. That's a good one.
Do you have numbers for like clearance on either side of the boards, like for the Phobos and the Mars board? Like,
They should already have it because it's mainly just the GPS on the back side and the SMA, which is the highest point on the other side. Unless the caps that are over on the sensor portion end up being higher.
we can have that like for the.
That's like a known thing. No, like the clearance is a known thing, right? It's not.
It's in the
Okay.
3D CAD that I
It's in the-
like,
Okay.
and you can let me know if it's not. I'll tell you whatever. Or you could just literally do whatever the SMA height is.
And then for the JST connectors that are on the board.
Yep.
The
The 90-degree ones.
90-degree ones, how much sturdily are those attached? Like, is it possible that? Like, is the only attachment the solder?
I'd be more concerned if they were like underlying. There are different pads that can be like completely covered, like some of the sensors are coming. I'd be more concerned, but we can like load the sides up with solder. And we can also consider putting like an epoxy layer, like. What else?
I don't think
No, we were doing through holes before. But I was thinking that for the caps, because like, you can't really see the caps that well, but there's a little nub that comes out on the side, and it might be beneficial if you want epoxy or super glue or something. Yeah, it's probably not super glue, but.
Okay.
Let's see.
Thanks, you. Like the gun potato. Whoa.
Picture. We're going in front.
I got into the table.
This is the worst censoring. The screen.
Yeah, oh, it's becoming I think
In
one line.
one line, you're in like layers.
There you go.
Yeah, everyone's legs out and touching the table so that you don't get the projector.
You still got.
Okay, so you in the middle have to go on one at a time.
Oh.
That's a big problem.
It does.
A square.
Just want that one. Yeah, there you go. Square. Just on the table.
We're photogenic.
Sorry? Sure.
Everyone ready? All right, we are the separations crew for the two-stage rockets. Overview of what we are doing. Overall, we have the role in making the sustainer motor retainer, and also a couple of staging systems. The first is the stage mating system to create a positive connection between the sustainer and the booster. And then the stage separation system to disengage the stage mating system and physically force the two stages apart. And then finally, the sustainer ignition system to fire the charge, which actuates this stage separation system and ignite the sustainer motor. What we've been doing since PDR is overall just improving our PDR design, designing the motor retainer overall, designing interfaces between everything, and the focus of this term overall has been manufacturability, calculations, and transition design. Overall, the linkage system changes since PDR. One of the main things is on the outside, we've made everything a lot smaller. We've also revised the linkage system a lot, and we'll get into different layers of everything in a second. The external view here, overall, we have the external layer for the separation system. At the top is the sustainer tube. Below it is the transition that contains the motor retainer, the tail cone receiver, and the tail cone. It is important to note that the transition and the tail cone underneath only contribute to aerodynamics and not load bearing. And below that is the booster tube that contains leakage and piston systems. Next slide is the, if we look under the body tubes, we have the tail cone receiver, which is a single piece of aluminum, is attached to the linkage system and is designed to hold the tail cone until separation. Below that is the mount to combine the tail cone receiver and linkage system, and below that is the piston and support structures, structural supports. Peeling away the transition and the piston tubes, we can see the contact points of the inner structure of the motor retainer, as well as the radial fins that is pushed by the piston at the bottom. And finally, the last little section is peel away the piston itself. We can see the thrust plate, the motor retainer, and the linkage system keeping everything together.
Then, and then the overview of the sustainer retention system, we chose to go with an in-house design as opposed to a cost option such as an Aeropack. It was made to make it much easier to interface with the separation system, and it has three-way radial symmetry, also matching with the separation system. There are dual aluminum bands for locating the sustainer on the tail cone receiver. The inner one remains with the system at all times, and the outer one, is removed. Analogous to the part that screws off on an Aeropack retainer, and to remove redundant components, the lower outer portion on it, which would be this the lower part where you can see the mating connector still in this image. That is where the piston interfaces from the lower part to force it up. So here's a more detailed view of the lower assembly. Those red lines at the bottom are where it separates during integration, putting emphasis on this is not where a separation point in flight. This is just where it's taken apart during the integration process. There, you see those are there are those 3 sets of standoffs. The lower set and that lower aluminum band and the retainer plate all stay together, and you take them off to to remove or insert the motor. Once again, that'd be analogous to the part of an aero pack that you unscrew. And then the middle and upper standoffs transfer load into the rest of the sustainer with the thrust plate interfacing with the upper lip on the motor casing. And more detail on load paths are depicted here. On the left, there's the load path under thrust, both from the sustainer and the booster, with blue arrows being booster thrust and red being sustainer thrust. And on the right is the maximum parachute deployment load, and blue arrows are load path there. Calculations: each set of standoffs has had its ability to survive maximum compressive, tensile, and bending loads verified. The lowest factor of safety on any of those was 32. The minimum size of those is being constrained by the diameter of the bolt we're using as opposed to material strength. And due to complex 3D loading, we determined that FAA would be necessary to validate the integrity of various parts, especially that lower band, which per some SolidWorks FAA, we determined that it would survive with a safety factor of 5.
As mentioned earlier, the tail cone is a single piece machined out of aluminum, which provides a reference for the geometry of the sustainer tail cone, just so that the 2 parts fit together basically just like a glove. Because when the booster portion lands, the top portion of this tail cone receiver will be hitting the ground most likely first. There will be a thin composite layer around that aluminum just to make sure we don't ding up the aluminum so it can be reused later. The bottom portion of the tail cone receiver has dowel pins, which ensure good clocking during assembly and to make sure that the sustainer and booster portions do not misalign later during flight or at any point after the initial assembly. The receiver mount, which sits underneath the tail cone receiver, secures the tail cone and centers it in the body tube, and contains 3 different linkage core fin holders at the bottom, which will be discussed a bit more later. As for some of the calculations we did, using a bending moment calculator, we determined that the maximum bending moment would be 300 inch-pounds. And because we're trying to enforce a no-slip condition, we decided not to end up using shear pins because shear pins cannot on their own create that 133.4 pound preload necessary without the bending having already occurred, which is why our linkage system helps with this, as it creates the force before the bending happens and therefore does not end up with any reactionary forces. Some of the forces on the thrust of the sustainer, the largest force that it'll go under is about 238 pounds. And because this force occurs after which there may be a little bit of relaxation inside our design, so we cannot always necessarily assume this 238 is a constant. But to ensure we surpass the worst case scenario, during separation, we'll assume we have to overcome this entire 238 pound force. And under the relaxation, when the linkages fire, we'll assume that there is complete relaxation and there is indeed no force.
Okay, so in order to provide that preload, we're using this linkage. You saw a version of this during PDR. It is now reduced down to a 6-bar over center mechanism, works the same basic way where the green and yellow link there provide a over center toggle that locks the whole thing in place. And as the piston moves up, it kicks that horizontal extension, actuating the whole thing, as you can see in this video here, and pulls the retention pedals inwards off of that flange. Major changes to this since PDR, we've moved from actively controlling the angle of that engagement plate to it is now a passive conformal surface. We've flipped some of the link locations around. More things are tucked into one another than used to be, which helps on vertical space savings. We've moved to this radial fin core design to mount it instead of the tall pillar it was on, which introduced flexibility concerns. It's much more rigid now. Some small changes to how it's actuated outside the rocket, but mostly we've been focused on figuring out details of manufacturability and performing analysis on the loading of this. So starting with that engagement block there, you can think of this as analogous to on a C-clamp, that little wobbly bit that makes sure that it's aligned with your workpiece at all times. This just gives you a few degrees of relative motion in order to make sure that any small tolerance errors, you're still going to get that line-to-line contact transmitting your forces between the flange and the main link there. So looking at the other links and how they would be manufactured, because there are a lot of parts to make for this, in order to simplify things, we focused on what are really the key dimensions of these links, which are the relative locations of your pinholes, because that's what drives the kinematics of the system, and the tolerance of those pinholes themselves. But we don't care so much about locating those holes relative to the outer perimeter of these parts. So the plan is to quick make blanks of them through either outsourced manufacturing or a router, and then precision ream the bore holes to get them exactly where they should be and how big they should be. As mentioned, we've moved to a completely new way of mounting this. We have this aluminum hex core. The center part there is it's a COTS hollow hex extrusion. It engages with these 3 radial fins that constrain it in the center, and it just slides in from the top there and is retained by a single bolt. So as was mentioned at PDR, if we ever have concerns with the viability of the linkage and we want to say, okay, we're just going to shove a bunch of shear pins in this, deal with that, you can anytime from minutes after this presentation to moments before launch, pull that bolt, pull it out, you never see it again. So the pins used in this they're a combination of press fit and slip fit into the links. We've done analysis to make sure that over our temperature range, they will maintain that press fit and slip fit behavior. And the connections to ground would be done through shoulder bolts just so that you can pop one off, pop on a replacement. This is a detailed look at the over-center geometry. You can see kind of the line of action there highlighted in the pink and blue lines. We went with a 5-degree over-center just to make sure any latent vibrations or whatnot can't shake it loose. And a big change from PDR is it is now actively forced through the entire range of motion rather than trying to work in some kind of spring assist. So that tip of that kick link there, that only slips past the piston at the very end of linkage travel now. External activation, still done in 2 phases. Top is same as mentioned at PDR, you kind of lever it down. We've moved to these threaded inserts to do the final locking though, for a couple different reasons. It helps make sure it's always aligned. You can get more torque out of it, which allows us to shorten it because otherwise the length of that reaction surface is your minimum height. And it allows us to have functional remove before flight tags because you do not want those in there when we fly. Getting into some of the numbers of this, we did a MATLAB script to do the static force analysis of the linkage. We can experiment with various configurations, assumptions for coefficient of friction, and so on. One of the things we did with this is assessing the increase in force that comes from that brief moment when you're overcoming the over-center, when you're actually briefly forcing it down, and what that does to the pin forces. It ends up being only about a 40% increase at the first one. And we used that to derive the full forces on all the pins and all the links, and plugged that into a spreadsheet to assess them in tension, compression, shear, bearing, tear out, combined bond species, pin shear, and pin bending, and they all have pretty great factors of safety. We've also been working through tolerance analysis to assess how errors in manufacturing would affect the position of that engagement link. The results we've had so far suggest that we might want to make some of the links in the over-center a bit more compliant so that there's a larger range of distance over which you're achieving an acceptable preload.
For the piston, it consists of 4 parts, an aluminum pusher plate at the top, the body, which we're planning to make out of nylon tube stock, but we might change to 3D printing if we have to. An aluminum seal retainer, which just retains the O-ring seal, just keep the gases or the pressure in the piston tube while it is actuating, and a fiberglass bulkhead at the bottom that is what the force from the piston charge or the ejection charge will actually act upon. The pusher plate at the top is there so that the piston will apply an equal force to the entirety of the sustainer flange. And it also is removable too, so that way you can easily access the linkage which is in the center of this piston. And then the slots in the body tube allow the hex core fins to pass through it as the piston actuates, and they also act as a hard stop for the piston at both ends of its trackle. So these are some we did some calculations for the piston and the charge, or the force, the charge required, and all that. So the pressure needed for the separation of the booster and sustainer is 30 psi. This comes from the energy needed to accelerate the sustainer away from the booster, and this 30 psi is calculated ignoring the kinetic energy of the piston, which is the worst, which gives us a higher force required than if we had taken that kinetic energy into account. The amount of black powder needed to reach this pressure is 1.3 grams. Currently, we are doing the calculations with this 30 psi to make sure that all parts of the piston system will have no issues. For the parts that we have finished the calculations on, they'll all be overwhelmingly fine with that at 30 psi. It's the piston tube. It's a 4.5-inch fiberglass tube made by Wildman. It holds and guides the piston throughout the duration of the stroke. It's going to be mounted to the coupling by a centering ring that is epoxied to the outside of the piston tube. So it'd be that blue line right there. And then all the holes and cutouts on the piston tube are just clearance only. They are not used at all for locating any part of the structure. Oh, that's. This is, I don't know what is there. Mainly for the piston sealing O-rings, the outer diameter of the actual couple is 4.375 inches, according to AS 568 standards, which is aerospace standard set by the Society of Automotive Engineers. We can use groove dimensions that are 0.049 inches deep and 0.084 inches wide, with a corner radius of 0.008 inches. And to create an ideal seal, O-ring should be stretched by about 2% up to about 5% ideally, giving us an ideal inner diameter for the O-ring to be about 4.193 inches. This can go down to create a larger stretch, but you don't want to reduce it too much because you want to stretch it too much. And then this is just cross section of the connection between our subsystem and the structures coupling. So the centering ring bolts to the forward face of the coupling and forms a seal, allowing ejection gases to fill the open volume of the coupling. And then overlapping our systems in this way saves space and also saves weight. And then this is a test bulkhead. So because of the challenges with testing black powder, we will be using a test bulkhead to simulate the ejection charge. So the initial test will be made with a screw pusher to actuate the piston. And then following tests will be made with compressed air that will better simulate a black powder charge.
Initially, we were told we were going to be responsible for lighting the sustainer motor. And so we came up with a design which used a Blue Raven altimeter in the mechanics bay and a limit switch, which you can see in the diagram there, to detect separation with some of the charge wires going over the separation point. However, apparently some wires may have gotten crossed, and recovery found out that they might be responsible for doing this. So our biggest thing is now figuring out who is specifically responsible for ignition of the sustainer portion and getting things worked out from there.
Questions?
Let's get some maps first, I guess. He has better examples than something I do. Slide 43. He said the holes look like they might. Said the holes look like they might break the material, so the edges might need to be increased.
You mean the axial holes?
Yeah, I want
Those holes on there.
the holes in the CAD look like really, really close to the.
Oh, the counter bores.
Yeah. But
Okay, I think those probably could be pulled in a little bit. That said, there really isn't any kind of load going through that inner wall there.
So what is this made out of? That specific piece is
Aluminum.
Aluminum.
Aluminum. So when you bore those holes, do you know how close those holes are to the end of the wood?
I was, but yeah, you're not going to be able to machine those likely without breaking the material.
So those are counter bores. Those aren't through holes.
You're still going to be using the machine, make them, and it'll still cause a lot of vibrations.
Mhm.
Even with a kind more while you don't need to abide by the very thing with the kind of board, I definitely recommend increasing that distance. It looks like some of them fully intersect with.
Okay.
The other thing you could do, I guess, would be just slot it out, go the other way and do like a semicircle slot out. Because again, you're not really depending on that thin webbing to accomplish anything. It's just there as a residue of what the diameters are.
Question. Yeah, let's put a slide. So, do you have any idea of the weight of this? I don't know what that's.
Specified.
It's a number.
I believe the last we checked, total mass was, I know he was asking for with and without linkage. It was like 5 point something total. The linkage itself is only 0.6. The bulk of the mass is in the transition receiver and associated coupling. There's definitely lots of opportunities for lightweighting on both those parts, but that's really what the mass driver is.
Well, how much, yeah, I missed this, but how much force is needed to activate the mechanism?
Oh, you mean that, what it takes to trip it?
Yeah.
I forget the exact number, but it's somewhere on an order of a tenth of what you're achieving in preload. So very small. And the limiting factor on that is the actual ejection force. So we've been working off of that as our constraining number. Because you get really extreme mechanical advantage at that spot.
That was my question.
I have a couple of clarifying questions.
All right.
So clarifying, is this drag separated or do you have an injection charge?
I know that that piston will be hitting the this bottom plate and it will be forcing it out.
Yeah, we glossed over it a bit since it was kind of the focus of our PDR, but you see that little tab there. As I actuate this up, that's what pushes on that linkage tab.
Yep.
So you're epoxying in the hex key, like into the airframe?
No, we would be epoxying in the like threaded insert.
Okay. So
That's purely a function of I couldn't find ball end set screws that were long enough to be external to the airframe, so you need something to extend it.
okay. So it is something that you connect to after.
Yes.
In case you need to scrub and take it apart.
So for launch, that entire thing comes all the way out. It is not on board the rocket.
And then we have this slide, 67. I think we do like paths.
No.
So if you guys end up doing payment for recovery, this comment won't happen. Like, if you do end up doing it, absolutely need a backup.
Yes. Essentially, the plan for that would just be an exact duplicate of the system, but with a different header.
Okay. One last lab. Could you go to slide 48, please?
All over the place.
No, it's more about this one.
This one has a video.
Oh, wow. It wasn't 48. Shoot.
Well, we get to watch the video.
Once you have the tail cone, that's gonna be aluminum. And tell me then.
I also don't have memorized where everything is.
Yeah, I like wrote down the slide like after you gone past it. That one.
Okay.
Just what are your manufacturing plans for the deep?
It's unfortunately going to have to be a very big hunk of aluminum that would put it on the lathe.
Yeah,
It's going to be a pain to manufacture. Not in the sense of we think it's like not going to be super viable to do, but just it's going to be like two fairly large operations.
Yeah, and we are aware it does need one main op on the C30, which would be the outer inner profile and all the radial holes. There will need to be a second op on the reverse side to get the axial holes because there's no way to get a drill diameter without hitting that.
Cool. I just need to know. Because obviously a lot of this is like next year.
Yeah.
Yeah.
Pretty much every part has a back of mind how it's being manufactured.
Mm-hmm.
We've been making sure as we go we aren't designing anything stupid, but CAM is definitely the thing we have to do next over break and such and really lock it on.
And then I have one last question. Sorry. So it sounds like this is like a pretty modular system, but do you have an estimated time to assemble when and also like the assembly done before or long before?
It's going to require a substantial amount of assembly, but most of that would be done well before. In terms of integration at the launch site, it should it should primarily just be the fact that we need to wait to put in the motor is going to be the biggest limiting factor. But once we can get after that, we can pretty much just get the charge in the charge well, put in the piston linkage assembly, close that up, and then put the motor into the stainer, put that down over the linkage assembly, arm the linkage assembly, and then we're good.
Also, I would add to that the answer is going to depend a bit on, if you look at our Slack, there's a big message about a bit of a conflict we have to figure out with how this integrates with structures, and depending on how we go about solving that conflict, the answer to what has to be assembled launch day versus can be assembled weeks, months ahead of time may change.
Yeah, but it's not like we have to assemble this whole complex linkage system day of.
You don't have another PDR.
Oh, wait, okay.
Any more questions?
Well, Gorilla Small.
Oh, wait, maybe? Yeah, no, there is one. I forgot. The original, screenshot
Oh, okay.
That's good. We got that presentation all by yourself.
Yeah. With how the Wendy meet was looking for the first couple of days, I was worried I was going to be doing something.
You got that.
Yeah.
Yeah.
Okay, when I was entering the building, like, I was actually saying.
Yeah, they do.
Who I just told you yes.
Included accelerometer.
This says M1 and 2 plus have accelerometers and gyros. One of them is
Only blinked in half of them.
Hey, I probably bring in the other half, so good luck.
We good to go? Want to wait a bit? Good to go? Cool. So, good evening to the large crowd we have here. We're Payload Recovery, and this is our 2025-2026 CDR. Our requirements for this year are to eject the payload at 850. Yeah, Amber. Okay. Are to eject the payload at 850 feet with a secondary charge at 750 feet. We'll have a 26.1 feet per second descent rate. We'll release the main parachute lines on landing with the EOI and attach a cord from the bottom of the EOI to the parachute to prevent reinflation after landing. Our timeline for the rest of the year is we're going to have our prototype of the EOI machined and load tested by the end of January. We're going to test and ensure the hexacopter is flight ready by the end of February. March, we'll have at least one drop test to ensure the mechanism works, and then however many drop tests that like payload division needs. And we expect to have all IRAC components manufactured, assembled, and finalized by April, or by the end of April. So with some helpful feedback from PDR, we've decided against using CO2 ejection for this year. We're going to be using black powder because it's considerably smaller and lighter than a CO2 system, and also because we're not going to run into any issues with altitude since we're ejecting at 850 feet. So because we're using black powder, our wiring is very similar to previous years. Our two batteries are EPOC 18350, 1100 milliamp hour single cell lipos. On the sides of the sled, we have space for two battery boards, a spot tracker, and our two altimeters, which are one Blue Raven and one RC3 Plus. Everything has some clearance on the sidewalls to make sure we won't have any vibrations or other issues in flight. And some important dimensions for the recovery bay itself are its height, which is 3.9 inches tall, and its widest diameter, which is less than 4.2 inches. The piston, just like last year, will function as a type of form factor connector for the payload in addition to holding the parachute assembly. Although the inner radius is not constant, the average radius is around 2 inches, which makes the packing volume total about 50 cubic inches. We're going to be packing the parachute in first, which has an expected volume of only 18 cubic inches, and the ELI sideways on top of it, and then the rest of the shock cord on top of that. Some important dimensions for this are, just like last year, 4.5 inches tall, with an expected overlap with the payload of 0.5 inch. So the rest of the space for parachute packing is 4 inches. The outermost diameter of the piston cup is 4.6 inches. And as said before, the average inner radius is about 2 inches. The mounting holes are in the bottom sections of it that are widest to minimize space taken up on the bulkhead, and also allows for easier packing. So the piston design's main goal was to keep the payload's L channels lined up with the standoffs to make sure that the force of ejection was transferred properly through those L channels. The piston does that by preventing the payload by rotating with the extensions against whatever brackets that are at the end of the payload. The shock cord will run from the eye bolt on the bottom of the nose cone down the side of the payload to the piston cup, where it will be coiled and stored with the parachute. We're going to be making sure that the cutout, as seen on the right of the piston cup, is going to be lined up to the same side as the eye bolt on the other end of the payload. Our standoffs have not changed from last year. So using the standard standoff stress calculator and verifying buckling equations, we have a factor of safety of 5. We potentially could change the position of the standoffs to like maximize surface area between them and the L channels, but the piston cup survived a fall from the rocket last year, so I don't expect there will be issues.
So Gabe knows all about everything else, but I know about the ELI system. This is our parachute release system. You'll see later in the drawings, I apologize for the dimensions. I kind of eyeballed it from the online diagrams. The mass, if we're using steel, which was one of our options, is 206 grams, about 206.5. We had a last minute change. Gabe was able to talk to someone in Washburn who advised against using steel and instead using 75 aluminum, which has a higher yield stress. That is a bit lighter than the steel that we were planning on using in the first place. And there's some other dimensions there as well. We were able to run some simulations in SolidWorks to test for the stress. This one is with the aluminum. The diagrams that are up there are with the previous aluminum we used, so the force numbers aren't exactly accurate, but the locations of where the force will be applied and where the force will be felt are accurate. We calculated that there is about a 65.98 pounds per foot total force applied, and this has a factor of safety of around 10. The force was placed on the overhang of teeth as the two parts will be separating. Yeah. And then this was the simulation from the steel. It is a little heavier, but it is able to handle a bit more force. I don't think that factor of safety is entirely accurate. I did do the calculations quickly. I apologize. And then here's our final drawings. Dimensions are as accurate as I can make them, and very detailed. So
for IREC and also for budgeting reasons, we cannot allow the parachute to be fully separated from the payload after landing. So we're going to be attaching a line from the bottom part of the EOI up to the parachute with either of the options shown on the slide. The reasoning that we're holding them up there as well as for why we're even releasing the parachute in the first place is to prevent the parachute from filling on the ground. So if the wind blows into the parachute before it is able to significantly pull on the payload, the lines shown here, the purple or green line, will deform it and basically make it so that it is not able to keep its form as a parachute while still pulling on the payload. Our testing, so we're going to be testing everything we make, especially the EOI. Before using it in a drop test with or without a dummy payload, we're going to be testing it with we're just going to be load testing it to ensure it's strong enough to take our worst case shock loads in flight, and that the detachment mechanism consistently works both with and without those high forces applied to it first. From there, we'll do drop tests of the parachute with the dummy payload to verify descent rate. And then we'll bring it all together with some drop tests with the hexacopter as well. The parachute we're using, we're going to be using a Fruity Chutes 36-inch compact parachute, which has a coefficient of drag of 1.6 and a packing volume of 18 cubic inches. The descent rate that we have here is calculated from is calculated directly from the Fruity Chutes websites, where we inputted the expected 8.5 pound payload. As mentioned before, the maximum shock force we expect in the worst case scenario, which is the rocket main doesn't deploy and we're moving 80 feet per second at deployment, is just over 57 pounds. If everything goes as expected and we come out after main, then the expected max shock force is 13.82 pounds. Yes, and that is all. Yes.
Yes.
So cover the ejection height for just the yeah.
The ejection heights, from
The very beginning.
the very beginning, partially is what we used last year. I remember also the bottom limit for at least one of our altimeters was around there. Yes.
So
70 or 78.
And this time I'm getting So I really don't know how. However, I would do it. Not, I don't. Sure that it is very. Just this simulation.
Yeah.
And I have one more, if you could go to, well, actually, it's.
81.
I lied, but.
80, yep.
I might not be able to see, but I don't. It doesn't look like they have color.
I do have some, I did put some tolerances in here.
Oh,
Yeah, I know, it's a really small diagram. I don't blame you for missing it.
So it does the, detaches, it just, obviously, the water under the tension and separate.
Yeah, so when not shown in these diagrams is there's a spring in the like hollow inside part. So before the parachute is fully deployed, there's a case holding onto it. That case gets pulled off, and the tension of the parachute holds it until it hits the ground, and then the spring like pushes them, separates it.
There's a pin.
Yeah, so there's a pin that goes through.
So this hole right here has the pin holding it, and it's up against the casing. And then that pin pushes the casing out, and then it detaches from there. Yes. Yes, that's with the spring.
The like worst case of if this doesn't detach is, I mean, we can test. I don't, worst case scenario is just it acts like the, it acts like it's just part of the rope, which wouldn't be great, but is also not the end of the world. And this also would work for like, if the parachute like starts going down at an angle, all it needs is just a moment to separate. Yeah, we can look into that. I would hope that if it's windy enough for that to happen, we're not shooting a rocket off, but.
So the Eli mechanism has a lot of weird angles.
Yeah.
Do you have a plan for having this be fixtured or manufactured?
I don't. I think that's something we have to figure out, because I kind of just eyeballed the angles. They are, I did put even angles in. They're not like something weird. I think it's 60 degrees from the top. Yeah. But we have yet to figure out how we're going to place that in the machine to manufacture it properly.
In the conversation with my friend in Washburn, I received, I was told that we like would be able to fixture it. I wasn't told specifically how, but we will work on that for over break. Sorry, the question for a while.
Yeah, and maybe I'm just like not understanding your drawing super correctly, which requires that. So, do you have any concern about like if the whole point is so that it doesn't inflate on the ground, right?
Mm-hmm.
Do you have any worries that that could happen under the net, like that it will?
So the importance of the line is that it's being either attached to a point on the canvas of the parachute, expecting like through a loop that is sewn on by the manufacturer, or just by going around the parachute. That line should be, or is planned to be, there's planned to be enough slack in that line so that it shouldn't interfere with the parachute during the descent. And then because it's attached from the parachute to the bottom part of the ELI, that'll become the like, that point of connection will become where the parachute is like pulling on the payload, which the visual metaphor I've used is like holding a trash bag by the like bottom of it and trying to use it as a parachute. Yeah.
So, experience, what happens to, first of all, that loop does get tangled. See that, I'm guessing that's the swivel at the bottom of the system.
Yeah.
What happens if it gets tangled by below? It looks like there's quite a few things on that swivel. And
So-
then it pulls the parachute.
So the line is going to be like, it'll be like swivel and then I believe like a swivel to a quick link with both the ELI and the like bottom of that line. The real answer is this is like part of why we're going to be doing drop tests with the just parachute on its own, as well as like with the ELI, like with the hexacopter, is to see if experimentally we can get that to happen, or if it tends to not happen or fix itself. That would be catastrophically bad if it happened, is your point.
Yeah, I would just say, make sure, no matter how many drop tests, even if you just do a test, like, I wouldn't test it until you know it works, test it until you know it won't fail. Because that does seem scary.
We did an amount of this last year as well, and didn't run into any significant issues, although I don't think we ever got to do anything more than a pull test. So we will make sure we do that.
Yeah, for machining as well, I was wondering if it has to have, like, if it has to be cylindrical with the ELI, as opposed to just square on the edges. Might give you more material. Yeah.
Yeah.
Instead of like a pill, if it was just like rectangle.
That's a great suggestion. We would definitely think about that. We machined this, we designed this only based on the plans we saw on the website, and theirs was a pill shaped, but we definitely can consider doing it, like maybe just a high angle chamfer on the edges to make it a bit more square and less cylindrical. So. Okay. All right.
I'm really jumping around, but have you considered how like attaching extra lines and
Yes. This is something that we did last year as well. We tried both like wrapping that line in as we rolled the parachute and trying to keep it separate. With pull testing that, neither seemed to seriously what's the word? Harm the ability for that to happen. But as with a lot about the line placement stuff, we're going to be very rigorous with how we make sure or how we test.
Okay, that's good.
In terms of the lines of the parachute, I'm also envisioning when it's, when it's deploying, there are, so the parachute has lots of extra lines attached to it. The big loop, which I do think is the better of the two ideas, because of the big loop, because it has to have so much extra slack in order to not contain parachute during deployment. Seems like those lines could very easily just get whipped around the regular shroud line, and you end up with an accidentally partially reefed parachute. So just, I guess I'm just saying, consider that too. The other thing being, you definitely want to rigorously test your stitching if you somehow try to attach an extra line.
Yes, the attaching extra line to the parachute. Some of the parachutes we have came from the manufacturer with that loop already sewn in. So my hope and understanding is that that wouldn't be a concern, although we can definitely make sure.
Slide 71. Looking at the boards.
Mhm.
Battery should be aligned horizontally. Just so that
Okay.
Is there enough room for them to be rotated that way?
Yes, there should be, in worst case scenario, if we need to swap which face the battery boards are on versus the altimeters, I don't think that would be a problem. Or, yeah.
Another question about the batteries. I'm just curious. I know you mentioned like a specific model of battery. Is there a reason like that one specifically instead of the 18650s that we have?
I believe these are the ones that we have.
Oh, do we?
Is it 18?
350s, yeah.
Maybe I misread. I thought the city. I just when I looked it up, it was like a with that. Well, I just looked 100 milliamp hours. Oh no, it's 350. That makes sense. I thought it was 650 now. It's like that's not that much capacity.
Any other questions?
Maybe I missed this. Is the piston cup bigger than last year?
The piston cup is the same as last year. Yes, if we don't have other questions, Kate, I actually have a question for you. With the, oh no, you did actually explain why you favored the option 1 versus option 2.
It's a little safer.
Mhm.
I guess maybe I would say just tempo.
Yeah.
I can see you good.
Thank you.
Thank you.
So like why so but like why the well, it says there's not necessarily. So the, but then it says because the one I don't think it's but it says we never know. But again, yeah. That was my question. Why the like so what is it? Separating. That's what it is. We're releasing the lines. That's the. I'm like, oh.
So typically, I'm just saying.
So I know. I just see it. You know what you're saying? I'm just saying that you can't go. That's why what you said. You just said it's making a line. It's line being like so. So line release it. The same. No, but if the device, if the device releases, if the device releases in the air, I think the point if the device releases in the air, we are not in the air. Yes. It says abstract release devices. / cable cutters. Yeah. It's crazy. Oh, yeah, actually, yeah. This is what we proposed last year, wasn't yeah. Well, the team two is. But SRS might have. And I think the phrasing is more.
All right, let's go start.
So I guess should just make sure that that's.
Okay. Hi, this is the GNC CDR. I'm quickly going to go over, as a reminder, our goals, and we'll go into the hardware for our canards rocket, and then talk about some improvements we've made to the EKF and a change in controller we're working on as well. So just a reminder what we're trying to do this year. Trying to create best practices for C++ and MATLAB for GNC for future conditions, as well as perfecting the EKF and seeing how far we can go with that, and getting this canards rocket to be a very successful launch. So timeline-wise, how we've lined up with this, there's been some slight movements around. The MEKF has had some robustness improvements in MATLAB, and we are in the process of testing and implementing in C++ and seeing how that correlates with the lift data. MATLAB-wise, that looks really good. The controller, we're switching to an LQR controller, so that needs some work to kind of redo that algorithm. And hardware-wise, we're ready to start manufacturing after this design review.
For computer fluids, we finished the simulations for a variety of different air brakes. You can see all the way on the right is the current air brake design that we are using on the two-stage rocket. And then we're looking into an extended air brake and also a shorter version. And they all have different deploy angles. So the current air brake that we're using has a deploy angle of about 63 degrees. And it's about, 120 millimeters long. And then the extended would be 170 millimeters. And the shortened would be 90 millimeters. And then with the extended, that's with the shorter length, so it doesn't deploy as far. That has an angle of about 72 degrees relative to the airstream. And then the short one, that's about the highest deploy angle we get. That's 54 degrees. And unfortunately, my laptop with the data broke shortly after I finished running the sims. The data is intact. I've not gotten my hands on it to process it and get actual numbers out. Hopefully it'll be back by the time winter break starts. And then I'll have numbers probably by the time we come back.
The hardware for the canards architecturally has not changed much since PDR. The guiding principles are still the same. We want a platform for which to test the guidance and controls, research and development that the controls guys have been working on. And the key attributes to accomplish these are a modular system that flies on a proven rocket and is able to be adjusted for future mission goals. Just to recap the architecture, we are still going with a 3-deck design with a bunch of 3D printed structure and metal clamping plates at the top with a modular quarter system. So each canard is basically part of its own modular independent quarter of the assembly that can be slotted in and taken out if something breaks or we need to change something up. The canards themselves can also be hot swapped onto the rocket without having to disassemble still. And the multi-deck design is still able to slide into the Voyager rocket and stabilize itself without need for a whole lot of extra hardware. One thing of note, we are sticking with the Voyager rocket with J500? With the J500, I'm sorry. We did run into some issues. The number we gave at PDR, 271 meters per second, we're actually going to be moving 271 feet per second. So there's a little unit conversion error there. We're still going around 1,000 feet, not going to be going anywhere near supersonic, which is probably for the better. But if anything, we did design around the requirements of going that fast and with those forces in mind. So if anything, the system is just probably over-engineered at the moment, which is good because in the future, we're planning to go faster. The batteries are still slung underneath, still mounted horizontally in order to make sure that when we see acceleration Gs and stuff, we don't lose contact and run into any power issues. We're still looking for the COTS battery holders where we might end up 3D printing our own. Regardless, we need 2 batteries to be in series and the other 2, and somehow the 2 holders can be in parallel. So we maintain around 7.4, 7.5 volts out of these 18650 batteries. The servo deck 3D print did have some changes. We clocked the switch a little bit differently to allow for better wire passage, which I'll show in a photo separately. But other than that, we did get our hands on a servo, and fortunately, it was almost the exact same as what the manufacturer advertised in terms of hole placements and dimensions and stuff. Just had to make a couple minor changes. And yeah, this system is still the main structural component for the lower deck. It will be a pretty close tolerance on the inside of the coupler tube for the Voyager rocket. And so with this structure down, slung below, the canards should prevent the whole system from bending. Servo selection, again, has not changed. I'll go over the reasons why we chose this particular servo again, because it has all metal construction, so no plastic components transmitting power. Pretty high torque, especially for a servo that can fit in the palm of your hand. 197 ounces per inch, 0.06 seconds for 60 degrees. And they are about $40 each, but that's about on par with what else you can find in this range of performance for a servo. The canards level themselves have also undergone some minor changes from PDR, mostly regarding hole placement and how we plan to assemble this and manufacture it. But the general theme is still the same with 3D printed structures. This is on the bottom right, you can see a quarter with the canard attached. It'll tab in and be pinned and slot with dowel pins to locate itself, and then be clamped on the bottom and the top by 440 sock heads going through the entire assembly with a lock nut on the bottom. This is still, the canard itself is still going to be accessible from the outside of the airframe. There's a set screw that comes in from the hole in the bottom right, and you unscrew that, the entire shaft will pop out, and you're able to hot top a canard. The canard itself is going to be pressed and likely epoxied onto the shaft, but since the entire shaft can come out of the assembly, we can switch out canards pretty easily. One thing to note, the center of pressure of the canard is behind or underneath the pivot of the canard. So if something mechanically goes wrong, or maybe even electrically goes wrong, and we lose a servo, and the entire thing is free to spin, the canard will go to a 0 degree angle of attack and shouldn't have any effect on the aerodynamics as long as the other 4 canards also go to, other 3 canards go to 0. Okay. There's a cross section. Again, not a lot of change. We are still planning on printing most of the structure out of PETG, but it does have steel going through the layer lines, shear pinning basically the entire thing together. So we're not expecting any forces ripping the assembly apart in that axis.
So here you can see kind of an exploded view of how this all stacks up together. You have in the gray that aluminum hex core that holds the canard shaft. The orange link is press fit onto that. The bearings react off of those turned surfaces on either side of the core piece. And the encoder mounts onto the face of the back there. The encoder is kind of the constraining piece for why we had to do this in this weird quarters segment, because if you assembled it together, there would be no way to slot the encoder in there. Well, it's just a square, especially when you take into account the wires. So with this structure, you inevitably get some thin sections in some of these prints. So again, we're using this parallel plate structure to hold it together. And a new thing we've added now is we have the Mars board mounted on top of this via standoffs. This is unchanged from PDR and was spec'd for 3 times the loading we thought, so I'm just going to zip through these. And we've gone through and made sure that all these parts are things that we can actually buy. So next steps will be final reviews of some of the very fine details that are too fine to get into here on hole clearances and so on. We're looking into doing wind tunnel testing of this. And once we get our computer back to life, we want to experiment with different canard sizing for the first phase.
So this is also a repeating slide from CDR, but we kept it in basically just to give everybody a reminder of what our Simulink architecture is like with the plant model and the flight computer. And so our MEKF group will present the flight computer stuff now.
Okay, so this is also a repetition of what we said in CDR. So we looked at the EKF from last year, but that is for mainly for nonlinear systems, and it doesn't take into account quaternions, which is why we are using an MEKF instead this year. So one of the updates we did was that we transitioned from trying to split the attitude and position velocity from 2 states and tried combining them into 1 state, because it would be hard to get position data from attitude, especially since attitude gives position data, and if they are not in the same state vector, there could be a buildup of errors. And additionally, we also tried to switch from NED to ECEF for many of our reference frames. And this is because ECEF is better for longer and higher launches. It takes into account the fact that the axes are not local, and it's also easier to convert to ECI. So yeah, this is.
All right, so we made a couple updates to the Simulink, including the barometer. So on the new MEKF, it's modeled more correctly, where you convert it from height to pascals, or you take in your estimate, you convert it from height to pascals, and you compare that with the measurement. So this allows us to get the Jacobian in native pascals and account for variance equally throughout the flight. So how we do this in ECEF is a little bit more complicated, where we have the the Jacobian of pressure with respect to ECEF is the Jacobian of pressure with respect to height times the Jacobian of height with respect to ECEF. We also use innovation gating for fault tolerance. In a couple of the rockets, like what's it called? We'll have the air brakes deploy and then two-stage. We might let some air in, so we want to be able to reject those measurements when barometer gets corrupted. So we use a chi-squared test to do that. Yeah, slide. Then we also implemented 2 IMUs. So we weight the IMUs based off of the variance, and our implementation is a little bit overcomplicated and overkill. It allows for any number of IMUs to be accounted for. In this, we do a linear optimization problem. We want to minimize the variance subject to there being no lever arm effect between the accelerometers. Luckily, this has an easy solution, and it's now implemented for 2 IMUs. Lastly, we use GPS velocity for orientation. When you're going really fast, you can assume that the velocity is in the inertial velocity is in the body X direction, and then you can correct for orientation that way. But we only use this in high speeds. Then also our absolute orientation determination algorithm, triad. We can use that on the ground using the accelerometer and the magnetometer. But then now with velocity, we can use that in midair. In case our EKF just goes wild, we can reset and take that. Yeah.
We also managed to implement our C++ code. So we have 2 stages, preload and launch. So in our preload stage, we mainly just take in data from the accelerometer and the magnetometer. And we also use something called the triad algorithm, which takes the average of the 2 sensor data. And if we have a GPS, we are thinking of setting the accelerometer settings to position, which can make it ready for launch. But if we don't have GPS, we will just run the MEKF using orientation, but then change it to position right before launch. And during launch, we will just run the MEKF. And if we do have the GPS, we will make sure that the unit norm of the velocity will be much greater than 0, so that when we're using velocity to update the orientation, there won't be errors in the negatives. So right now we have the main algorithm written, but we haven't really tested it yet. And this is kind of because it works like a hard drive. It's a general purpose MEKF that can be used for anything as of now, but we need to implement it with the canards and like the 30K and the 2-stage to get it working.
So time for some graphs. Okay, so with perfect sensors, so the MEKF priori update works. With perfect sensors, it has 0 errors in the attitude, in the position. However, it's not totally converging yet with noisy sensors. So as you can see, in midair with it does pretty good in the X direction because we're given the magnetometer data helps in the X direction, but the other 2 are not converging that well, and the covariance bounds are not encapsulating the error. Yeah, that's just in degrees, and then positions looking pretty good. And then one of our states is the accelerometer bias, which is also looking pretty good. So areas of improvement, we need to take the actual sensors and calculate their deterministic errors, stuff like scaling factors, misalignment terms, non-orthogonality. And we need to find a way to do this without like turntables and precision instruments. So yeah, probably more hardware and working with the electronics team next term. Then also we need to figure out our random errors. This is more important because right now our process noise is not correctly tuned. And honestly, I think our sensors in the Simulink are not working correctly. So we need to understand that more and do an Allen variance test to get the correct terms and be able to accurately model our sensors. Then just future side quests that we can do. Just test different edge cases, like launching in different directions, launching at different places, etc. Right now, we don't implement like the world models. We just hard code in like the magnetometer, or I mean the inertial mag reading and the inertial grav reading. Then also we can go through open source libraries like ArduPilot and PX4 and then see what they do. For example, I got innovation gating from that, so we can find what they do. And although not a big improvement, probably improve a little bit. Then other things like dual quaternions, ECI, and then looking at advanced GPS stuff. Now to guidance.
Yeah, guidance has stayed the same. Once again, this is a stabilization system, so the goal is to get all of our orientation rates down to 0. I'm not sure what that was. Okay, so basically, we found a really nice paper that a school in the UK published about using linear quadratic regulators for canard systems in amateur rocketry. And so we decided to switch our control system over to that. And I'm just going to provide a little bit of a justification as to why we think that's a good idea. We haven't implemented anything yet because this is a pretty recent decision, but I think it'll work out very well in the end. So in this paper, they ended up doing a robustness analysis that looked at how the controller behaved with a variation in the canard lift coefficient. And as you can see, it behaves extremely well in the sense that it continues to follow the nominal performance extremely well. Basically the black line is like the robustness performance, and then the yellow line is the nominal performance. And what we're looking at is the fact that the robustness performance is very, very close to that yellow line, and that shows that this controller works extremely well under variance. So in our case, where we're not like entirely sure if it's going to work well, this gives us some confidence that it's not going to have any really crazy commands based on just our like dynamics not being what we expect them to be. LQR controllers are also inherently stabilizing as well. And that's because it acts as an energy minimization problem. All you do is you essentially minimize this equation here. The X transpose QX, actually, I don't think that's a transpose. I'm not entirely sure. Is it transpose? Okay. Is a current energy of the rocket, and the U transpose RU is the energy associated with the control inputs. And so by minimizing that equation, you get a stable system, which is really nice. And it just acts as a pure gain matrix, which in MATLAB is tuned with a function, but we haven't looked too much into it, but there isn't like a function to do that in C++, so we're gonna have to find out with a way to tune that pretty well. But we're also planning on implementing gain scheduling, which is essentially changing the gain of the controller as the velocity changes. As the velocity of your rocket gets faster, your canards require less actuator effect, so we want to make sure that we're accounting for that in our gain. And we'll do that by calculating the optimal gain sets from the like minimal velocity at which the canards are functional to the max speed of the rocket. So another thing that we're looking at is the possible points of failure with the system. Obviously, we've never put like an active control system as volatile or as like just not air brakes on a rocket before. So we want to make sure that we're taking into account all possible points of failure. So a couple of potential hardware failures are that either the canards don't respond to the motor commands that they're given, or the commands are significantly different than your absolute encoder reading. So like if the canard gets stuck and you're reading a different value than the canard is actually at, then in that case, we should be able to read those in the controller that the like system isn't changing at all or whatnot, just based on like what the values of the encoders are at, the value that the EKF is returning and what we're expecting based on those. In addition, if there happens to be a software failure for some reason in which our controller diverges, resulting in in commands that will heavily impact the system, then as seen in the electronic CDR a little bit earlier, we're planning to implement an electric switch off to cut all powers to servo under the circumstance that that happens.
Questions? Yannick?
Slide 111, you talk a little bit about changing some things up, like pre-launch and launch. Are you just running on stopping your state estimators after seeing the apogee, or is that just like?
Probably not, but we just haven't been thinking about after apogee yet. I think when it gets slow, we can stop. Like we'll stop using GPS velocity for orientation, but otherwise, I think everything else is still the same. But yeah, starting now, we will think about that more.
I wonder if you want to look into like changing your process noise after you hit apogee, because like the process is probably a lot less noisy during launch. Like it's just motor. Then once you hit apogee, everything's spinning really fast.
I mean, I disagree. I feel like the process noise is really high during launch because we have an integrated EKF, like the really high change in like position, like you have to account for that everywhere.
Yeah, well, that's true. So I guess I'm thinking. Yeah,
thinking of the attitude spinning.
Position is, you're right. Position is higher noise during launch, and attitude is a lot higher noise during.
Yeah.
Descent. Yeah.
Why would you change your process noise? Like how do you think you would change your process noise?
Well,
reinitialize it while it's flying.
We just change like the function.
You just change
I see what you mean.
Yeah, I mean this is supposed to be. I mean, it's supposed to be like trajectory independent.
Yeah,
but that's something we can look into.
I guess that might be maybe dumb comment on it.
No, it's a good thought.
Yeah.
Other questions?
Do you know what to cite? So I'm really curious what the advantages of the like squared off and then slightly triangular slots. I'm assuming that's so we can disassemble quarters of the system together. That seems to me like an excess of unnecessarily complicated machining. And I'm curious.
Oh, these are all printed parts, that machining? Yeah.
So, 6. So, okay, I understand. So the aluminum is not everything involved.
Yeah.
So it does seem like if the tolerances are up just a little bit, it could be not very fun for assembly. I know one of our biggest issues a couple of years ago with air brakes that I'm not sure we ever really 100% got down for the new system for air brakes was that we had 4 parts that all had to meet in the middle. And we made them so many times and we never got it perfect. And so air brakes, they never quite extend the exact same amount. Seems very similar to something.
Yeah. One of the challenges with this is because the system is so space constrained, there was pretty much nowhere to put the threaded rods holding the whole thing together aside from where those quarters have to come in. So we had to do some funky geometry to make it so that that hole is whole, essentially.
I guess, yeah. The weird triangle shapes, like, is that just so that they slot together like a clocking feature? Is there not a simpler way to do that?
Yeah, I guess you could take out the Z clocking if that's a concern. Yeah, I guess that would work.
Well, to me, it just seems like, so you've got clocking in, like there's a slot in the middle and also that shape. Is that the only place it's being held into the circular shape? Is that because of that clocking? That seems.
No, so eventually what holds it all together is the axial bolts going through the thing. So
Then why do you need so much clocking in that? Presuming the Z-axis is the axis of the long axis of the rocket. Like, whatever. Why do you need so much clocking in that there?
We could probably get rid of that.
Because they're rotating and adding arrow forces.
Yeah, I guess the concern would be because there's so much going on these pieces, there are a bunch of inevitable thin sections. So anything you can do to promote load sharing is nice to have.
Oh, okay.
Okay.
For any aerospace people, I do have a question regarding system defense software. Does anyone have an experience with maybe some math algorithms to detect whether a good algorithm to detect divergence of expected values versus what we're reading? Like if the controller MEKF diverges, does anyone have an experience with that?
Well,
Maybe.
isn't that like what innovation is? Yeah.
Oh, okay, that's a good point. Okay, cool.
Yeah, because that's like one of the problems is like, how do you know if your navigation is good? But yeah, in theory, they need vision.
So long as you don't.
Well, actually,
There's innovation getting that you want to predict things that are not bad.
well, at that point, so if you're innovation meeting, then it's, I guess it's the program instead of,
That's pretty.
So you missed my comment.
It's not a change. It's actually
But you missed it.
This slide. Okay. So this presentation is going to be quite short, so we can all go home. There's a lot of people here. Anyway, true. We are Flight Software. This is a combination of rocket software and payload software, as we said at PDR. So here's what we're going to go over. Quick timeline, what we have gotten done and what still needs to get done. The state machine and how that's changed, although not very much. The sensors, which have changed a little bit more in some implementation ways, but not in functionality. What we're doing for reliability and testing, which I'll talk more about later. Data logging, since that has changed a little bit from last year and we didn't have a plan for it at PDR, but now we do, and we've tested it and it works. And then integration with other teams. So timeline-wise, A term, we got everything set up as needed. Some of that went to B term, that's fine. We got a working system ready for the lift launch, and it had some minor bugs that we have now fixed. But that's done, so we're now ready for launches in C and D term as well. The one thing that didn't quite get finished in B term is unit integration testing. So that will continue in C term, ideally soon as possible in C term, a little bit potentially over the break. So then in C term, we can finish up features that were not ready for the lift launch, like radio communication and payloads, various servos and their mission. And then we will set up and use our testing throughout the whole rest of the year so that we know that any changes we make are good and didn't break anything. So we're as ready for a launch as we are now. Cool.
Okay, so the state machine, like we said, doesn't have many changes. So it's remaining just a function per state that takes in data from the sensors and the rocket and produces whether it should there should be a state transition or not. Some changes that we're making since the test launch. There's a lot of common functions that happen within each state that we're going to abstract away and simplify, so we don't have as much redundancy there. And also more state-specific data that specific to each state, because right now it's a lot of general data that's shared between them, which is not really what we want. The 30K state diagram is basically the same as it was for PDR, but we have some, we decided on the state, what will cause the state transitions here. We don't have any numbers for it, but you can see sort of the flow of the states that the rocket will go through for that.
Our two-stage diagram's also basically the same as from PDR, but we did add a few indications of what causes the next stage. And one other thing is that in the separation stage, there will be a coast beforehand and then a coast after. And one thing that's not confirmed yet is that we might have a wiring mechanism to better indicate when the separation actually happens.
So for sensors, nothing is really changing since PDR. We plan on using basically the same thing going forward, just there are internal changes we'll be making based on lessons learned from Lyft and feedback from Rohan. Thank you for that. Yeah, so like the goals are the same. We want to be able to do testing with them by feeding in data from past launches. Yeah, allowing us to like change a sensor and we don't need to change it too many things. So the one change from PDR though is how data is accessed. So originally we wanted data access to happen in Sensor Manager, which is really hard to do apparently. We don't want to spend the time on that. We want to finish this and move on to other projects. So what we'll do instead is what flew at Lyft is data is accessed from the sensor itself. It worked well. It's easy to do. So that, and for reliability and testing, we'll be doing this in C term. We're going to do a proof of concept of uploading code to like the dev board of the chip that we're using. We're also doing like same things like simple code, make sure it works, that type of stuff. But the running code on the boards when like a merge request is made or pull request, whatever they're called, that'll be a C term project. We'll do a proof of concept over break, make sure it works, and then yeah.
Okay, so the way that we're logging data has changed since last year. So last year we had basically a fixed rate logging that logged all the sensors at one time, but that had the possibility of missing some readings from sensors. So this time we have individual packets logged in a binary data file, and they are at the polling rate of each sensor. So then we have a parser to decode that binary data that's logged, and then separately from that, we're also logging the timestamps of each state transition.
And so just, these are the same slides basically from PDR, what integration needed to happen, what actually got done. So electronics, they've got all the sensors we're going to use. That's now been confirmed and figured out, and the wiring all works for us. So ground station wise, there's still the new radio module driver to do. Ground station is working on that. And we will need to like formalize and decide on the format of data we're sending. That has not yet been totally finished, but will happen pretty soon probably. And some of that we can take lessons from the SD card, stuff that we changed. So Last year, we used protobufs, and we may use something similar or something a little different this year. And then payload integration also looks pretty much the same as it did at PDR. We're writing the overall code base and handling the states that get the payload up and back down. And then once it's landed on the ground and all nice and stable, we, along with the payload rover subteam, will write the rest of the state machine for the payload's actual mission on the ground. And you can see a more in-depth view of what that state machine looks like in their studio, which may or may not have already happened, I don't know. I guess not. But we'll be writing that along with them and giving them any help they need. And that is all. Questions? Yeah.
Good slide. You guys say like large upward acceleration and small upward acceleration. How do you guys plan on determining those values?
Yeah, well, so part of the reason there aren't like values or specific things mentioned here is because we don't know yet. I mean, we did at Lift just use the direct readings from the accelerometer, and that works. If there's an existing EKF, we may use the values from that where possible. But like right now, large upwards acceleration just means one of the accelerometers gives a big reading upwards for a long enough time. And small upward acceleration really means like negligible or negative because there's drag.
I'm looking at using velocity instead. If that's what
we can't use velocity until we have the EKF. So we will if there's an EKF, but not before.
Because acceleration is.
Yeah, we won't get acceleration out of the EKF. I'm saying if we have an EKF to read from, we'll use its values like velocity. But
second question is on 30. So you guys log with the timestamps, right?
Mm-hmm.
Like, do you log UTC time or just like
elapsed time from boot? But one of the things that's logged is the Unix epoch from the GPS, so you can correlate them. Like
you don't have GPS.
Yeah, then we can. I mean, the board does not know the time, so if we don't have GPS, there's no absolute time. Anything else?
So actually, GPS time is logged separately, right?
Yeah, it's logged when we get GPS data, but then if we get one, we know.
Yeah, well, I'm just thinking like if GPS is every second and you're recording 1,000 times a second, the other stuff, then like you don't have, I guess you just rely on the timestamps being like.
Yeah, time doesn't drift like that.
But you're just relying on the duration of each loop being consistent, like in between the GPS measurements, which is probably.
But you know the time between the GPS measurements in milliseconds, and you also know the time.
You know the time between each.
Yeah.
Like reading, but then the time between each like magnetometer reading in between the GPS readings.
But you know those times in milliseconds too, because there's always a relative time.
Yeah. Well, I'm saying you're trusting the clock is stable enough.
I do. I do trust that. Time doesn't drift like that. If it did, more things would go wrong than just.
Yeah. I'm just thinking. Well, I guess it depends on how often you're. I mean, some of the sensors can record at like 10,000 hertz.
But over a second, the milliseconds clock isn't drifting. Yeah. What, Nick? Millis right now, but we could do something. Nothing's gonna wrap in the time we're. Okay, so we don't want to do that. But 64-bit wouldn't. So I just don't think we care enough. Yeah, this is true. At the moment, we're not. So. Yes.
Other questions?
I just have one more thing about like the.
Yeah. Maybe I'm just misunderstanding what you're saying, but.
No, you're right. I'm just probably overthinking. So for the state machine, so you said there's no longer a sensor manager, right? Well, there's a sensor manager that's in charge of What does the sensor manager do?
It makes sure that polling rates are held like consistent to each individual sensor, so we don't overpull. Getting the data itself, the sensor will hold like the last packet that it read, it's like successfully. Well, last packet that it read when the manager told it to read it. Okay. So you would get that. So when you go to read, you're not polling it. Only the sensor manager will poll it.
And then, so what's responsible for logging the sensor readings?
Some other system.
That isn't the state.
Yeah.
Okay.
I guess it could be the sensor manager technically, but right now it's just a separate function.
Okay, that makes sense. I was thinking, just based on the diagram, you had all the sensor readings going in just the state machine. And
Yeah,
I know there's other stuff happening.
Right.
If that was
They
the case,
can be used by anything.
yeah, well, that's maybe not great for like abstraction, the state machine, scope changes. But if you have.
Run to do.
Okay. Bro, I'm already looking at it. I have classes. I need to do that first.
You got Monday.
No, I don't. I have my grad course on Monday. Screw you and your.
It's unfortunate.
Yeah.
But it's compact, so you look at right now.
Yeah.
Okay, does anybody else have any CDR relevant questions?
I actually do have one more,
Okay.
just regarding the time stuff.
Yeah.
So you're logging elapsed time.
Yeah.
Can you also log the count?
Yes, although at the moment, so this will probably change. In the lift code, there was nothing with a relevant like loops to count because the state machine was running as fast as possible. I guess that could be relevant. Probably it will be running at some fixed rate and then we'll log the loop count and we'll see how close it is to the fixed rate. But like the thing logging the sensors runs as fast as possible and just only does anything when there's a sensor reading. But so I don't care how much that loops.
Well, it's looping.
Except on a time scale.
I'm saying like the loops don't necessarily correspond to like if there's a bunch of calculations, then the loops is slowed down. Like if you have the one processor, even though it's running as fast as it can, the actual duration of the loops could be changing.
That's true.
So it's good to have like the loops and then the duration that the microprocessor is taking.
Yeah,
in case there's like any discrepancy.
we do need to do something to make sure we're not like taking too long on any one thing or find a way to handle that separately. But I don't think we can afford to log every loop because it is significantly faster than we have like reasonable space for.
I just felt like we had weird things happening.
No, I know.
Like this last IREC where it was like, it seemed like it was like pausing. And so just more data we can use today.
This is the thing. This would be all of my purposes. It's your own map or kind of statement.
Yeah. Yeah. I mean, I'm fine with logging like a number of like actual cycles of the loop function every second or something. That doesn't take extra space and tells us a little bit. So yeah, we'll do something like that and do more testing to see how much it can keep up. Yeah, we can see if we've really broken something in terms of timing. Yeah, that'll be part of that. Okay.